Okay, hello everybody. Welcome to a new session of our seminar. This will be a special session. First, Daniel is going to talk, and then Héctor. So, what's the title? The title of your talk. In higher Hida theory.
Okay. So the idea of today and next Wednesday is to give an overview of the give the statement and overview of the proof, joining what all the talks that we had before in some way. Okay, so we will start from zero now, recalling some facts, and so today my goal is in fact the statement. No, I didn't write in Spanish, but. Okay, so now I will start with the statement. Then Héctor will start. So you know that this will be essentially the some ideas of the proof. The next 3 talks. Okay, so today and next week will be kind of we will try to be more kind of a conference talk in some way that will be 50 minutes each one. So we will cover kind of 2 hours. So 50 minutes, 50 minutes, 50 minutes, 50 minutes. So we will be a little bit more speed than all the semester that we were very more friendly, no? But today will be more tac, 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 okay? Okay. So there will be a difference with the rest of the semester, but the idea is to give an idea to cover more or less what is the idea of the proof. So at the end of the talk today, I will give more details about these 3 parts, okay? So let's start. So my goal today is just to state the theorem. Okay, so it's very, in some ways very basic, but it's good to be precise. So okay, so we have 50 minutes, so I will try to finish at 11, okay? A little bit before 11. Okay, so before to start, we need to fix a prime p. So we are p-ádic, no? So in all these 4 talks, p is a prime. Okay, so we are working there. Okay, so let's start with some. So I will introduce now that was already introduced by Javier, but the geometrical objects that we're interested on. Okay, so that is curves of curves without level at p. Okay, so this is the main object that we are interested, and let me introduce the object. So as I told you, this was introduced more or less by Javier, but not completely. So let me precise a little bit. So, okay. So let's maybe we have no good pen from here. So we fix bigger. We fix an integer bigger or equal than 3, and we suppose that p doesn't divide the level. Okay, so that was introduced by Javier. Javier introduced the modular curve of level gamma 1n. So this is something was a scheme over z1 over n. Okay, that is a modular curve, open modular curve. Oh, let me write open modular curve of level gamma 1n. Okay, so that was introduced by Javier, and in his talk, but he didn't explain. He had no time to explain what is another object, and which is not open, which we call the compactification of it is a proper curve. Okay, so if you do with some extra work, you produce some new object, which is the compactified modular curve of level gamma 1n. Okay, it is still a scheme over the spectrum of Z. You need to invert n to get some nice properties that I will state now. Okay, so another definition we will call D, that will be the divisor that we need to add to obtain, to compactify in some way the curve. So this is the cusp divisor, no? Divisor given by the cusp. So I will write like that. But you need some extra process, some regularization maybe. Okay. These are the objects that we care. This is our main object that we're interested in. This is the divisor given of the cusp that will play an important role here. Okay. Some observations. No pen is reasonable. Maybe this one. Remark. Okay, some remarks about these curves. So firstly, as was pointed out by Javier, this is satisfy a moduli problem, no? So Javier gives the moduli problem given by this one, but we have also a moduli problem given satisfied by this one, no? So what is a moduli problem satisfied by this? That parameterize elliptic curves with some structure, you know? So let's just state for take R Z 1 over algebra, okay? Then you look at the points of this scheme, these R points of this scheme. So normally you write something like that, okay? Okay, which are the points of this scheme? So these are tuples, something like that, where E, now you remember that was by Javier, he said that this parameterized elliptic curves over a spectrum of R. That means abelian scheme of dimension 1 over a spectrum of R. But here they are not now abelian schemes of dimension 1, they are now generalized abelian scheme. There are some fibers are not really elliptic curves. Okay, so this is a generalized elliptic curve over a spectrum of R. Okay, and what is this iota? This iota is very important to have some moduli problem. If not, you need to work with some other geometrical object called stacks. Okay, but we are working with schemes. Okay, so what is this? This is the structure attached to N. That is it's a morphism between the following group. So you take Z over NZ. Okay, this group, you look inside the N torsion of this abelian scheme. Okay, and this is a homomorphism, so 1-to-1 homomorphism. In English, I think monomorphism, maybe people say something like that, of a scheme of abelian group of. So it's of, I have in Spanish, I may need to change the order. So of étale finite group schemes, yeah? Of étale finite groups schemes. So you parameterize that modulo isomorphisms, of course, okay? That is the moduli problem satisfied by this curve. That is more or less what Javier introduced last time. Okay, that is the first remark about these curves. The second one is why we invert N. So where these curves have good properties. So let me state the good properties. Okay, so if you have any questions, so just ask me, yeah? Even if that is, we're trying to do 50 minutes talk, so you have the right to ask questions. Okay. Okay, so what is the second observation that I wanted to say? That, okay, this is a curve that's been scheme of relative dimension 1, okay, with some good properties. But one of the good properties that I like to point out is that this scheme is smooth. Okay, it's smooth. Okay, that is important. Okay, so now let's introduce the notation that we will use over these 4 talks. So this we are trying with Héctor to be compatible. So notation. Okay, so here there is nothing p-adic. So the prime p that I introduced looks like not useful. So the notation that we will use is the following. So let's, before to introduce the notation, look at the following. So p doesn't divide n. That is our choice from the beginning. So n is invertible in the p-adic numbers, no? So you have that when you look this is inside of the p-adic numbers. So then in terms of schemes, you have a map. This is lives over the spectrum of this. Okay, so that makes sense to introduce the following notation. So that we will use over all the talks here. X will be the following scheme, will be x1n that we have here, which is kind of global, no? Because you have several primes here. You look just over ZP. So you look at the base change over okay. So that is a notation that we will care the most here, and we are interested in the cohomology in some way of this object. This contains the p-adic modular. This contains modular forms and produce p-adic modular forms, etc. And we are interested. Higher Hida theory try to study the cohomology of coherent cohomology of this one, of some precise shifts that we'll introduce in few moments. Okay, so before to introduce this shift that we are interested, let's do a picture of this that is good to keep in mind. A picture of this object. So X, okay, so let me do this here. So X lives over, so by definition lives over a spectrum of ZP. So we are, okay, but a spectrum of ZP have 2 points. So you know that you have, if you look at the definition, this is a spectrum of QP union disjoint of the spectrum of FP. No? This point is kind of bigger than this other one. This is closed. This is an open point. So the picture that you need to have in mind that this is the generic point which attached to QP, and this is the point of the special fiber. Okay, so you have 2 fibers, one attached to each point. So you have an object here, you have a map here, you have the curve there. Okay, but the curve we like to think about them. Here is you can think like a Riemann surface maybe. It's not totally true because it's algebraic. If you take, that makes some sense if you want. We are just playing with pictures that make help a lot, but okay. So you can think about it as a Riemann surface. Maybe this point is too big to. Okay, this is the open. Okay. Okay, and now you need to look at the special fiber. So the special fiber will be something like that. Okay. So the special fiber is parameterized. Now you compare with this part. So the special fiber parameterized elliptic curves over FP, and this parameterized elliptic curve over QP, and that together is the curve that we're interested in. There are some special points here, which are called supersingular points. This is supersingular points, which are attached to supersingular elliptic curves. That will play also, those points will play also a role in the proofs that you will see in the second talk today by Héctor. Okay. Okay, that is a picture we have in mind. So now let's. Okay, some question. That is the geometrical picture. That is the curve that we're interested in. If you have some question, please. Okay. So now we have this, and the second. Put one maybe. Yes, two. That was the geometrical object we're interested in. Now we need to. I say that we're interested in the cohomology. So we need some line bundles that we will introduce. Line bundles and cohomology. Okay. So now I will be more precise at which is our goal, maybe. Okay. Okay. So this is the construction that was maybe introduced by Javier too. Or we discussed a lot about several times. So just repeat a little bit to be precise. Okay, so you know that as this satisfy a moduli problem is a fine moduli problem satisfied by this one, you have a universal object. The universal object is some elliptic curve over X. So an abelian scheme over X is a generalized abelian scheme over X satisfying some properties. And you have also some structure at N that we don't care right now. Okay. Okay, that is the universal object. So we will do some manipulation with this. So this is a group. So you have a map here, which is the units, no? This is unit section, no? You can think about this section like the zero of an elliptic curve. No? You need a zero element, okay? And you define the following definition. So the modular line bundles we care are the following. So the modular line bundles. Oh yeah, I think Javier spoke about a little bit about that. The line are the following. So, for example, let's introduce in two ways. So omega E, because it's depending on phi, just put some E here because it's depending on phi. But we will call this omega always. Put here because this notation we will use it in the future. It's defined by the following construction. You take, so this is in words, these are the invariant differentials of the elliptic curve. Okay, so you take the differential of the elliptic curve over X, which is a bundle over E. So then you pull back to X and you get the invariant differentials. Okay, this is the one modular sheaf, and in fact with this you produce all that you care more or less, which produce modular forms. So if you take K in Z, you define omega K as K times the tensor product of W. So here I need some precision because what mean for K equals -1? Yeah? Okay. Okay, so this is our definition, but I need to precise something here. No? So observations. One is that this omega, in fact, is a line bundle. So that makes sense the title, okay? So that is invertible. So if omega is a coherent sheaf of X, now I'm introducing using the notation of Héctor, so that we connect these different talks, okay? And it's in fact a line bundle. What mean is in an OX model, which is of rank 1, so it's invertible, okay? Then that makes sense. So makes sense, okay? And then you know the definition of -2 is just taking tensor product of -1, etc. So that makes sense to that. Secondly, so as this one is a line bundle, so each one of these modular shifts is also a line bundle. Some people call this invertible shifts, so it's line bundle or synonyms, I think. Okay, so which is our goal? So now I have everything to state the goal of this Hida theory and the goal of these 4 talks, more or less. Okay. Okay. So how can I say so? Goal is to. How can I explain this? Say in a good way. Okay. So we are interested in the following ZP models. So these are really ZP models. So we will consider this one. We care that one, just the global sections. As we said before, these are correspond to modular forms. Okay. But also we care about H1. Okay. The Hida theory only consider this one. By higher Hida theory, consider also H1. And some modification of this by when you add some poles, you allow some poles on the cusp forms, on the cusps, okay, and this divisor. We're interested in these ZP models, and more important, try to understand how they vary with K. Okay, their variation with K. So you vary K between the integers, so you want to understand how they vary if you can put them together in some kind of big cohomology. Okay, so that is the goal that we want to try to address during these talks. Okay. Okay. So to do this, we need some operators, and maybe I have time to speak about duality, or maybe I have 2 seconds. So let's just state duality because it's interesting. Oh, I think I will avoid duality, but if I have time at the end, 5 minutes, I can state all the duality, okay? So let's remove duality by now, but at the end I will speak about Serre duality, you know, in this case, because it's algebraic. Okay. We have the geometrical object. We have a goal that we want to address. So now how we try to understand those models. So an important tool are the Hecke operators, and more importantly, the Hecke operator at P. To construct the Hecke operator, we use cohomological correspondence that were introduced by Héctor. And then we need a new modular curve. Oh, maybe I put 3. Oh, okay. I put 1, 2, no, the section, so that should be 1.1, 1. Okay. Okay, so curves of level with level at P. Okay, so this is you need to consider this curve with level at P as a tool to perform our goal. Okay, okay, which is this curve is very closely related to what Javier explained us, but with some modifications. So firstly, we take we repeat the same procedure. So firstly, we consider the modular curve of level gamma 0, gamma 1, n. No? That was the curve that open curve that we considered till now. But we add level at p. Okay? We add gamma 0 level at p. And that is again a an scheme over z 1 over m. Okay, this is an open modular curve of level, this level. Okay, again, we compactify that. We compactify this curve and we get something that we call x again. And the notation, as you expect, so will be, so, okay. So the notation will be, we will call, so this is global again. So we consider this at p as we care. So we call x 0p. So as is the model, this curve, but we base change to again to zp. So will be the base change to the spectrum of zp of the spectrum of z1 over. Okay, so that is a new curve that appears here that will help us to produce correspondence. You remember that the cohomological correspondence is another curve over your curve with two maps over your curve, satisfying some plus some extra data, which is a morphism. So let's go in that direction to produce this cohomological correspondence. So, but firstly, let's give some remarks about this curve that will be used by Héctor. I think this. You want a picture of it, no? Okay. Okay. Okay, so some observation before, so remarks. The first one is that this curve is not longer smooth. Outside the level, you have smoothness, but in the level, when you are for primes on the level, it's not smooth at all. So I will give a picture. So, but in particular, you have p in the level here. So you can again, so that makes sense again because it's defined over z1 over n. But this curve now is not smooth. You make the difference. The picture of x is very smooth. It's nice, no? But here, this one is not smooth. So x0p, xp is not smooth. Okay. And in fact, we can draw a picture to have a more precise idea. So again, so we have 0p over the spectrum of zp. Okay, you have again 2 points here. The generic fiber, which is spectrum of qp, the spectrum of fp. You have the generic fiber. All these curves are smooth when you invert p. Okay? In some way, the picture when you have the picture that you have over qp is something, again, something nice. You can imagine a Riemann surface without any singularity. Okay, this is smooth. So all the bad reduction, so the problem, the obstruction to be smooth is contained in the special fiber. Okay, so in general, you call this fiber of, this is the generic fiber, and this is the special fiber. They are folk names that people use. So what about this over this point? The picture now is not as before. Before was that, no? It was very nice, smooth, but now you have something like that. You have kind of 2 copies of the that you had before. And that is the picture that you have. So the bad reduction is not so bad. They are normal crossings. In terms of singularity, this is it's not so bad. You can work with log geometry and ignore this and think about them as smooth and work like, but okay. So it's not so bad. That is because p is just one time here, p. If appear p squared, the picture is not like that. Okay, okay, again, you have some points that here, these points that appear in these crossings, these exactly are the semi-simple, the supersingular points. Okay, so these are, again, the supersingular points. So that corresponds to elliptic curves over fp, which are supersingular. Okay, that will Héctor will be more precise about this distinction between supersingular and ordinary. But I just want to highlight in order you have in mind this. Okay, one more remark that I wanted to say. Okay, so about this, I think that will be used by Héctor a lot. So that, okay. So you have some kind of modulo problem too. Modulo problem. So now you parameterize some extra data. So for example, if take R, let's consider FP of QP, or maybe let's take that right now, okay? Then you have again a modulo problem, so will be x0 p. When you look at this, the p point, the R points of this stuff, R points are the following: are triples now, something like that. When the first two are as before, so the class of the first two are below to X spectrum of R, but the second one, this is a subgroup of the p torsion of the elliptic curve of rank p. This is of rank p squared, so you are taking kind of one piece inside. So a subgroup of rank p, and everything modulo isomorphisms. So some notation that we will use from now till the end of this series of talks is that we will ignore the level structure at n. Okay, so this iota we don't care about this. So so we will think points of X will be just elliptic curves, which is false. We need the structure of n, but we don't care. We will not touch during this work. Okay, we will just touch the structure of p. And points of x0p will be the elliptic curve plus some this subgroup C. But behind everything there is this structure of n, which is very important to have the modulo description. If not, doesn't make sense. It's just because it's not useful, I would just ignore. Okay. Okay. Now we have our tool to produce Hecke correspondence. Now we can introduce the Hecke correspondence. Okay, so now this. Oops. 4. So Hecke operators. So remember that the Hecke operators that we want to consider are over on X. Okay. Okay. Not over x0p, but x0p we will use it to produce them. Okay. So we fix some k integer. Okay. And we define, there's a technical definition that was done by Héctor, that was the finite flat homological correspondence Remember that Héctor gave two definitions. The first one was a cohomological correspondence also, only, but then a cohomological correspondence for some precise operators. So the operator that we care here is, of course, this modular. So for a precise line bundle, or coherent line bundle, coherent bundle. But our case is just WK that we care about. So we define as follows. So the cohomological correspondence have two data. The first one was an scheme, no? Was an scheme plus two maps. So not here, so we produce X0P to have this to be the scheme, no? So there is no surprise that we take a C in the talk, or maybe you didn't use C as in, I don't know. In the paper is C. So C will be this one, and you have two map to X, two natural map to X. One is we call P1, and the other one we call P2. These are very natural use traditional notation, but we don't care. And okay, what is so the P1? Take one point here. What is a natural map to X? Is just to forget the level at P. You forget the level at P and you get a point in X, as I told you here, no? Just forget the level at P. So this notation is very bad because I forget the level at N, but I told you, so it's just, okay? And what is P2? So the other possibility is to take care of C and don't forget it. So to take a quotient by this one. Both produce elliptic curves, and the level structure at N is fine. So you have some level of, because P is coprime to N. Okay, so that is the scheme. So now we need a morphism between chiefs. Do you remember? So that was the data of a cohomological correspondence. Okay. So what time is it? I have 15 minutes. I think it's fine. Okay, so we need a morphism, a map between chiefs. So if you remember the definition of Héctor, what we need is something like from P2 upper star of the chief that you care, no? Till this map that Héctor liked to speak about the formalism of six operations, okay? And in the definition of Héctor, it was called T, and by tradition we call TP, okay? So we will need to construct some map like that. So I will give some few ideas of what is the construction of this map. So to produce this map, we need to remember the definition of this W. Omega, in fact, it's a Greek letter. Omega is the invariant differential of the universal object. So consider the universal object of X0P. No. So no, you have a morphism, and you have several functors between. If you have something like that, no, between two schemes, so you have natural maps between the chiefs, no, between coherent chiefs. For example, you have pull back, you have push forward. And this part of these six formalism operations, sometimes, I think this one, you always have this one. No, okay. This one you have always. Okay. Okay, this one you not always have, but you have always this one. And they are related to each other by adjointion. Okay? But this is pull back, push forward, and these are more involved. So I have no. Yeah, I cannot give the definition now. I should know. Yeah. Okay.
The one that is exclamation is related with the duality, the chips. For example, to prove the star duality, you use this P1 exclamation And you this adjunction property, and then you, after conjunction, you will preserve to a person.
But the definition is, yeah, when it should, yeah. But yeah, it's also related with compact support cohomology, stuff like that. So yes, okay. So let's start with the universal object. And you have also universal level at P. I just gave the modulo problem before at points of FP points or QP points, but okay, you have a modulo problem also in you have a universal object. So fix the universal object here, and attached to it you have an isogenis between the natural ones. You just take quotient by C, no? That is an isogenis over X, no? Something like that. No? Okay.
Yes.
Here?
The last letter.
Ah, yeah. Okay. So you have this isogeny. By the way, I take advantage of it because sometimes you can use, in fact, the modulo problem of X0P, you can think about having some subgroup of degree P, or parameterizing this, or parameterizing elliptic isogenis of degree P. So it's equivalent. So in the paper, they use the modulo problem with isogenis, okay? But it's just to take a subgroup, you produce isogeny, okay? And you take an isogeny, you take the kernel, and that gives you the level. So it's equivalent. Okay, you have this isogeny, and then you can take, in some way, the map on differentials given by this one is in the opposite direction, no? You take the invariant differential of this, you have something like that. And this is exactly P2 take care of C. And P1 doesn't take, you don't care about C. So this is exactly the pi1 upper star of omega, where omega is the invariant modular shift that we introduced before over X. And this is P2 upper star of omega. Okay, so now we are closer to this one. Okay, so now what do you do? What is the next step? So now you use your K. Now you have we fixed at the beginning a K. So you take just tensor products K times this stuff. So you get something like P2 upper star omega K. Yeah. P1 omega K. If K is positive, this is a morphism. But if K is negative, you introduce denominators and you can have poles. So this is a rational map only. Okay? Okay. You have this one, but you have the trace of P1. The P1 is just to forget the level at P, and the trace of P1 goes from the structural shift of X0P to now appear this P1 upper star OX. Okay, this is structural shift of X, and you take this upper exclamation map. Proposition. If you take kind of the tensor product of these two stuff, you get the following map. You start with here because this is coherent, it's just the same. But on the right, you get P1, this one, okay? A priori, you have this one, no? It's a rational map. You have some denominators. And the proposition, let's state after. Okay? And what you care is about this map. So this produce this. So that is the TP. People use K because it's K, but I forget I remove K. Yes. And that is the Boxer-Pironi called naive because it's not the good one. The proposition is when you multiply, when the problem is with K is negative, there is not a map, no? So if when it's K is negative, you multiply by a good power, the power is the following. You know, if K is negative, this is a positive power of P. So you remove the denominator. And that's, this new map of chips is really a cohomological correspondence. So it's a homological correspondence. So that is a proposition that constructs the cohomological correspondence. To prove this, you need to take care of the curve and to look at it and to understand the structure of the curves involved. X0p, more or less. Okay. Okay, so now we have the tools, and I will more or less state the theorem, I think, in a few minutes. So, maybe I will be 5 minutes late. So, I don't want to be late. Okay. Okay, so we get, just because the general formalism that was introduced by Héctor, we get some maps between the cohomology now. So this is a map between chips, but in really that get a map between cohomology that was constructed by Héctor. So you get maps that you call TP, now go from H0 to H0 X WK, or even for I, no? Yeah. X01. That was explained by Héctor. And we get this map, which this is called the Hecke operator at P. Okay, that is the map we care. So we will be useful to produce to perform our goal. Okay, some observations, okay, is that, okay, remark. Okay, the first observation is that, okay, remember that ZP, these are ZP models, no? ZP model. And ZP is not bad, it's a local ring which is Noetherian and is profinite. Then we can apply the theory explained by Luis, okay? In fact, TP is locally finite. That was introduced by, the idea is introduced by Luis, okay? And this is, if you think in terms of, I think that is kind of, when you speak about compact operators, it's kind of the same idea. I was thinking yesterday. And we need to ask Vincent too. But I think it's just, it's locally finite, what was introduced by Luis. And everything that he explained makes sense here because ZP is a profinite stuff. Then we can apply infinitely many times. The theory makes sense there. Okay, what's more, there exists Hecke operator for L doesn't divide N and P. Or for other primes, you also have Hecke operators. Okay. Okay, that is, we have our object that we care. Now, this is the tool that this operator is the tool that allows us to perform our goal, which is study the cohomology groups and the variation with K. So now I will state the theorem, and the rest of the talks will be to understand the proof. Okay, so finally, five statement of Hida theorem. No? So, firstly, to make sense to the statement, we need to give meaning to the idea of a big a big space where we can have all the K's together some way. No, our goal was to study this cohomologies varying K. Well, what's mean varying K? Where we put that? So that is the definition, is the Iwasawa algebra, no? Is what contains this idea. So the Iwasawa algebra is the following ring. Is we will call in these talks will be that is a group algebra over ZP generated by the group ZP star. That is the usual definition of group algebra stuff. Okay. Remarks. Firstly, this is a ZP algebra. Okay, it is not local, it's semi-local. Okay, profinite. So let me explain why it's profinite in a few seconds. It's semi-local, Noetherian, and complete. To be more precise about complete, let's explain this. So let's M be the following. You have no a maximal ideal, but you have this some intersection of these maximal ideas, which can be described, I think, in this following way. With the kernel, you have a natural map from this. Just take quotient by P and take the quotient by P. Yeah. So you have natural map from here to FP, and you have a natural map from here to FP star. Is correct? Yeah. Okay. Because yeah. It's correct. Yeah. And this stuff play the role kind of the maximal ideal that we will care. So this will be the limit over n of lambda over mn, and this quotient are finite. As you see, this quotient, the quotient by im, for example, is this stuff which is finite. And okay, then in this, for this lambda, we can also apply the theory of Luis. Theory of Luis. It was introduced by Luis. Okay, so I'm almost there. So sorry for the minutes that I'm. So our goal with Héctor is to give an example that we can be on time, but again, I'm not going on time. I will be 5 minutes late, maybe. Okay. Okay. The second point is the idea of this container all the numbers integers. Okay. So fix an integer. Okay. And how this integer is inside this Iwasawa algebra is given by this following prime ideal. No. And consider the following map. So consider, we call SPK, we'll go from this to ZP. Is the ZP algebra, the ZP algebra morphism given by, so you remember that, so as a ZP algebra morphism, you don't care about the definition of that because it's clear. Just care about, you need to give the definition of where is the image of that. So you take some unit and this go to Z power K. Okay. So this map is called the specialization map usually. Okay, at K. So now when you have a model over omega over lambda, you can produce a model over ZP. Okay, and now you have the notion of to be big and contain all the K's at the same time, given by this one. And now we can state the theorem. The theorem, this is that is Boxer Piloni. That was written in 2020, maybe something like that. The paper was published in 22. No? Okay, and the statements say the following. So there exist two models, M and N, two lambda models, such that one. Okay, so now I hope that I gave the idea what this lambda is big, contain all the case in some way via these specializations. Okay, so these Mn are lambda models. So a priori they are big. To guarantee they are big, you need some condition of the models. There is commutative algebra, so you need at least something. 3 is too much, no? It's very, very nice, but projective is enough. Are projective lambda models they are projective lambda models. Okay, which is very good. In fact, they are projective lambda model of finite rank. So why? Okay. That is very nice. That give you the idea that they are big. They are kind of copies of lambda, even if they are not free. But that is okay. You have also there exists Hecke action on M and N. Okay, M and N have an action of the Hecke operators. Okay, and finally, so with that, I'm just saying they are reasonable models. But the interesting point is the following. So there are isomorphisms. Oh, because I'm translating from English to Spanish, and now from Spanish to English. So there are canonical isomorphisms, which are the following. I state that, okay, such that if you take k bigger or equal than 3, you have the following. So M parameterize. So you have this big model, and you look at it as a ZP model. You make it smaller, and this parameterize in some way the H0 cohomology. Okay, so the group that we care, but not all the pieces. It's not possible, but the part carried by this projection, the projection given by TP. That is a notation introduced by Luis, I remember. And the second one, N, take care of the H1. So you make these big models smaller of ZP model, and you can compare with the cohomology. And now it's the same. So you parameterize the H1. Oh, I wrote this in a way that is good for shared duality, but okay, I had no time to. Okay. And that is the statement. There is canonical isomorphism of ZP models, which are equivariant. So you have a Hecke action here, you have a Hecke action here, so you have here and here, which are equivariant for the Hecke action. Equivariant with respect to, con respecto a, the Hecke action. Okay, and one more point that I don't have time to write is about you can interpolate also shared duality, but I have no time to do it. So that is the statement, and that is what we want to prove during the next talks. So that's
Is there a question to our first speaker? Okay, if not, now is Héctor turns to speak.
Yep, estamos listos.
Okay, now we will resume. Héctor, please.
Okay. So, okay, thank you. So, before I continue, I want to just specify a little bit more what we will do in this talk and the other ones that will be next week. So the first one, I mean, now we'll talk about the mod P theory, you know, the special fiber part of the story, because we were talking about, you know, over set P. And now we will concentrate on the special fiber. And then in the other talks, we will continue with p-ádic theory, I mean, the big shifts theory, and the final deconstruction and some ideas of the proof, okay, of the term that I'm erasing, okay. Okay, up. Okay. Yeah. I erased this line because, okay. So as I said, I'm going to talk about like the mod P theory, okay. And so why we want to study mod P theory? So the idea of Boxer-Pironi is, in order to construct this model that Daniel just talked about, is to consider to take the p-ádic completions of the special fiber, okay, along the special fiber. And so in order to do that, we have to start with the special fiber, because we want to do a p-ádic completion along the special fiber. So we have to start with the special fiber itself. Okay, so that's the idea. So that's why we want to study so we have x, okay, and the spec of CP, and we take the special fiber that we say that's FP, and here I will make a notation for the special fiber that is x1, okay. Okay, and so that's so we want to concentrate on this part. This is the special fiber, or what we call also mod P theory, okay. So actually, I forgot to say that the idea of the theorem is to consider the ordinary part of the p-ádic completion of the ordinary part. So the first step of this talk is to talk about a little bit about this ordinary part. So what is the is ordinary locus, I think. Ordinary locus. So this is the first, okay, this is the title. So let me define this a little bit. So analytic curve, an elliptic curve over a algebraically closed field algebraic closed field of characteristic P. Okay, these P are the same, okay. Is ordinary if the torsion points, okay, the K point of the torsion point, okay, is isomorphic to set modulo. Okay, and this is FP, okay. Okay, set modulo P.
Small k is your close algebraic.
Sorry, over close K of characteristic P. So here's the K, sorry. So, okay, so this is the definition. So this is the one elliptic curve is ordinary when we look at these distortion points, and this is just a cyclic group of p elements. Okay. On the other side, we say E is super singular if E is not ordinary. Okay. So it's just a condition on the torsion point. Okay. P torsion point. Okay, so let me do a small remark. Just to make it maybe it will be kind of useful, but if E is super singular, then the p torsion points are trivial. Okay, it's just one element. Okay, and this follows from the. I mean, this is something that works only in characteristics P, because multiplying by P the elements of the elliptic curves is a degree P square map. Here we have in characteristics P, so we only have this possibility. Okay, because in theory it could be also the P torsion point could be P square. Okay, something of cardinality P square. And here, in this case, in characteristic P, where the only possibility is P or trivial. Okay, but this is some general remarks. Okay. In some sense, multiplying by P, in this case, the map is totally ramified. Okay, it have a lot of ramification. This is what it's telling us. Okay, so now so with these two definitions of these adjectives of elliptic curves, okay, we let X1 ort the moduli problem. Okay, I think that's how Javier called this of elliptic curves. Elliptic, maybe generalized elliptic curves. Okay, over FP. Okay, with level, we say we're going to ignore this. Okay, with level iota. Okay, but I just put it here in parentheses, so because this is just fixed, and since we fix it, we just I mean, what does it mean with level n? Okay. So so this is the modular problem of elliptic curve over FP with level iota. Okay, but okay, this is the normal one. Yes. That are ordinary over an algebraic closure of FP. Yeah. I mean, this definition was defined over an algebraic closed field. So we take an algebraic closure of P and we check if it is ordinary over there. Okay. So this is the X1 ort. Okay. It's a sub problem moduli of the one we start with, yes, with just elliptic curves. Maybe a generalized elliptic curve. Okay, so this is what I want to say. So let me tell you a little some properties of this submoduli problem. Okay, I put sub because so this is a small proposition. So X1 ort, okay, is inside X1, okay. It's as
Elliptic curves over K or over P? Over FP. Okay. Okay. Because I mean,
For example, these are defined over FP. Yeah. So. Yeah. Yeah. But the ordinary condition is checked on an algebraic closure. Okay. Okay, so maybe this is the first thing. Yes. So this is a sub scheme, okay, over of x1. So it's defined over FP. And the thing is that this is an affine open of, well, x1 and its complement is that we denote by SS. Okay, so these are two S. Okay, S. Yeah, because super singular. Okay, is a divisor of x1. Okay, and in this case, since we are working over FP, divisor just means a finite number of points. Yeah, finite number of points. Yeah, so x1 is a curve, and we are over a field, so dimension 1 is dimension 0. For example, in the case where we were in set P, these divisors are one-dimensional. Yes. Okay, so since we are using this, we're doing geometry in some sense, so we have to do pictures. That's the point of geometry, yes, I guess. So we can do some pictures. So now I have a lot of neat colors. I think this one should be fine. So, I mean, so this is maybe, so this should be x1, yeah, and we have some points, yes, some singular points. Yeah. Also, maybe I should first start with the ordinary part. So since it's an open set of x1, should be something like a part of the curve, but missing some points. Yes. And these are the red one are the super singular, and the blue one is ordinary part. Yeah. So this is just a small picture, but we will maybe elaborate more on pictures later. Okay. So that's what I wanted to define, like an open set of x1 of the special fiber that is affine, and that's all. And this will be the open set that will be useful in order to define in order to construct the thing that we want in the theorem, in the result that we want to prove, yeah, in the Hida theory. Okay. So these are the basic objects. So how we will construct these modules? So for that we need to introduce some cohomologies. Okay, so okay, I think I should use blue. So compact support cohomology. Okay, cohomology and correspondence. Okay, so we want to define these models that so what we to do in order to do that, we need to consider this compact support cohomology. Okay, so but this won't be so straightforward. Okay, I will explain a little bit. I mean, this is something that I mentioned when we will talk about the 6 operations. Okay. So note that since x1 ort over fp if you want is not proper. Okay, this is something about the compactness. So it's a fine. So it cannot be proper if it's not a point. Okay. So since this map is not proper, the definition of compact support x1 ort, I don't know, let's say the same, how do you say, modular chiefs, that was a name, it's not straightforward. Okay, straightforward. Okay, so this is a problem that we mentioned a little bit before in the six operation formalism. Okay, so okay, and this due to a number of reasons, but this is the one of the problem. But nevertheless, so it's a problem, but it's not an unsolvable problem. So let me give you the solution. Okay, let xic x1 ort wk to be. Okay, so okay, let me just write the definition. The limit of h1 x1 wk minus the divisor n times. So this is the definition. Okay, I will explain some things, but okay. So the definition of this cohomology group with compact support is this limit. Okay, and this is where some people call this direct limit. Okay, if you want, you can write this like this arrow. People put an arrow in that direction, but we just put limit. Okay, so this is direct limit. Okay, so this is like the limit appearing in the p-ádics numbers. Okay. Okay, and here we have x1 ort, that is the open affine of x1, and here we calculate this with the cohomology of of x1, of the whole space x1. But then we need to put, I think, zeros on these modular chips. So, and then we have to consider a limit of all of this. Okay, so and so why this appear in some sense, because we know that x1 is, I mean, I think we didn't mention, but x1 is proper. Okay, this is actually a compact thing. As we say, yes, we say this is x1 is a compact thing. Sorry, where?
You are moving n.
Yeah,
right?
I is fixed. So I is just an integer. Okay. Sorry. N is moving. Yeah, N is moving. So we're considering more and more zeros for poles, and I will kind of get confused. Okay, poles on the singular, and the super singular locus. Okay, and as I was saying, the point is that this one is proper. So we compare this one with something that is proper, but the price that we have to pay is that we have to consider zeros on the complement. If you, as I say, SS is the complement of x1 or x1 ort, okay, inside x1. So this is why kind of this look like this. Okay, we go to something proper, but we have to pay the price in the complement. Okay, so that's kind of the idea. So observation. Okay, so wait, I'm a little bit confused with so observation. So it's kind of what I was mentioning. So the cohomology of compact support x1 ort wk is a profinite fp vector space, okay, vector space, okay. So in terms of structures, okay. Okay, so poles. That's okay. Yeah. I always get confused. This is I'm putting poles or putting zeros, but I think we're putting poles. Okay. I mean that's what it means to adjoin this divisor in this current shift. Okay, so in terms of mathematical structures, the price that we pay is this adjective, okay, profinite. Yeah. So this a little bit more involved vector space. Okay. Yeah. So this is the space that it's like the basic space that we will use in order to construct this space coming from Hida that we want for the Hida theory, higher theory. But this is not the only one. We also need, maybe another. Sorry, we also need the honest, I would say, cohomology. Okay, we need H, the whole scene without compact support. Okay. But okay, this one is kind of involved. This is just something that is defined. Okay, I mean, we don't need to use all this procedure. This is just coming from general nonsense. Okay. But in this talk, I will just concentrate on this part because this is like, you know, it's a profile of FP vector space, so it seems more complicated. Okay. So let me put the main result that I want to discuss. I don't know where we're going to get, but let me just express this result. Okay, so proposition, which is this is just corollary 4.5 of Boxer-Piloni. Okay. 4. There should be a point there. Okay, whatever. So it's a corollary, but I put a proposition. Okay. So for k less than 0, we have locally finite endomorphisms we have a locally finite endomorphism TP that goes to H to the cohomology of the compact support X1 or WK X1 or WK. This should be fine. Okay, so okay, let me just write the result and then we comment some things. Furthermore, sorry, I guess this is no, it's fine. Furthermore, so ETP HIX x1 ord wk is isomorphic to e x1. I will explain in just a second. Just let me just write the statements. As I say, xi x1 o x x1 w sorry, not w o x minus ss up. I think should be fine. Once okay, I forgot this here, the C, the compact support, and the other one I'm not sure, it should be a compact support one. Let me check. Yes, I miss in my notes also a compact support. Makes sense, yes. I was talking about compact support. So okay, so this is the proposition. So let me explain some bits of these propositions. So the first thing is that the first claim is that there is an endomorphism that is locally finite. From the theory that Luis developed, or Santiago developed, we can define some kind of projectors, okay? And this ETP is the thing that Luis Santiago defined in his talks, but this was all on the hypothesis that the endomorphism should be locally finite. So this is the first statement, that is locally finite, and this allows us to define this thing. Okay, so, and this makes sense in some, thanks to the first part. In the right-hand side, I think, yes, here we have the TP, but this is not exactly this TP, yes, this is the TP that Daniel defined, okay? And okay, and what we were claiming, and this vector space are the same, isomorphic. Okay, so this is the proposition. Okay, now let me see. Okay. Yep. So maybe also while I erase, I forgot there is this a version of this proposition for k. So here k are non-positive, okay? But there's a version for this for k greater than 2, greater or equal than 2. And here we have to change the, instead of C, there will be non-C, there will be just the cohomology, and there's some very similar result on this topic, okay? But when k is greater than 2, we don't need this compact support. Okay. Okay, so so this is the let's say the main proposition. Okay. So let me just give you some ideas of how to prove this. So they will be used later. Okay, it's a key result. So okay, good. So ideas. Okay, ideas for proposition. So ideas for proposition. So what we have to do? Okay, first we have to maybe define the endomorphism, because these are like weird, I mean, this limit of things, okay? So the first step, one can argue that is just define and then endomorphism. So the first thing, that's definition, and also we will talk about continuity, I think. So this is the first, just define the thing, okay? So how we define? Okay, it's actually quite straightforward, because from what Daniel told us, we have this P2 star WK. We have this this correspondence.
One observation maybe in the statement. So the first isomorphism is for k bigger than minus smaller than
Yeah, true. Sorry. Yeah. This is for k minus 1, and this is k equal to 0. Okay.
Yeah, the left is for good ordinary.
Yeah, here also ordinary. Sorry. Yeah, so this is also a theme. Just here we have ordinary, and here we have the whole space. This is the affine part, and this is the whole space that is compact. Thank you. So starting with this, we can actually define, like just functorially, a map between just saying condition on the poles. I think was Ariel told me. Okay. So starting from the correspondence that we start with, that Daniel defined, we can just put these poles. Okay. And actually, so this is like the TPs that Daniel defined. And okay, I think the arrows goes in this direction. No, it should be okay. It depends. Yeah, it's this direction with WK minus N. So I will put a prime with blue, because otherwise who won't see this. SS P1 and minus N prime. I will put the whole thing. So N is greater than N prime, and these are greater than 0. So for every N, we have this morphism coming from the morphism that Daniel defined. And moreover, this morphism that we just are defined like functorially, in some sense, make this diagram commute, okay, for different ends. Yeah. So more negative, okay. Yeah, this is more negative, yes. Project to the less negative. And there's this community diagram, and this actually implies formally that we have a morphism, because we have a morphism between HI or CWK, HI or WK. One, I forgot the ones, okay. So this formally define an endomorphism, because these are just the limits. The pieces of this one are these ones, and for each of these one we define a vector endomorphism, and it's continuous because this is commutative. A continuous morphism.
One question maybe. One question about this condition of minus N SS. Are you sure that you're allowing poles?
Maybe I'm putting zeros. That's what I was confused. But
no, but you are defining compact support for homology of the ordinary part. And you consider the whole curve.
Yeah,
so
makes
you
sense.
want that this vanish.
Yeah. Okay. Yes. Yeah.
So you add a lot of vanishing. That means this vanishing go inside of the ordinary part.
Yeah.
So that it makes sense to
It makes more sense. Yeah. Thank you. Yes.
So they are not poles. I think you are asking more and more zeros.
Yeah. I agree.
So it's with the observation of Ariel, maybe.
Yeah, probably he meant then you allow, I think, zeros, yes, more than poles, rather than poles.
You ask for zeros,
Yeah.
Yeah.
I mean, the limit starts with n equals 0, so I mean, in some sense, is a limit, yes. So the element of this vector space, this profile is like an infinite, possibly infinite sum of functions that have zeros, more and more zeros on the singular part. Yes. It's like the p-ádics, yes. That's why I also say that this is the limit that used to define the p-ádics.
Are you saying it's a direct limit then? No,
It's
inverse.
inverse.
So I don't know. I mean, I get confused. I just use limit. Is it the inverse?
Co-limit is the projective, I think. I don't know.
I think it's a direct limit from that go from any speed that the section here is n is smaller than n prime, then you go from the cohomology of n to n prime.
Hmm?
Ah, no, you're right. It's inverse
Is it?
because you're taking a negative minus.
Yeah, it's like where function that have like probably infinite number. I mean, the zero can be very big, I guess, but controlled by powers. It's like the p-ádics, yes, you can put p square, and this means that it's getting zeros and p.
Yeah, just zero.
Yeah, but I like it. Yes, that's a good thing. Good way to remember. Yes. Yeah. Good. Now probably won't forget. I hope. Okay. So we have this we have the definition, and the definition actually implies continuity in some sense, because some abstract nonsense. Okay, or the definition. Okay, so let me give. What time it is? Okay.
When you say asking for
Zeros, you mean adding the roots? Vanish, like adding zeros?
I mean, not adding in the sense that. So, I mean, I will be very imprecise here, but how can we think elements here? Okay, so I will say this like a function that could be non-zero in SS, but I will put another function, but with something that is a power of SS that kills when I put an element of SS will be 0. Then I have another function, I know, okay, G1, G2, and SS squared. So I put a function that dies 2 times, have multiplicity 2 in the singular locus, and then I continue like this. So I mean, this could be G2 could be 0, yes, and could be,
So you're adding
Functions that vanish on the super singular level.
yeah. And I'm adding this infinitely.
Yes.
Because this can be, But the point is that the limit of this function that is getting increases 0 of SS will converge to 0. Okay.
You are saying that the global sections of omega are 0? Omega square are 0? I'm not.
Okay, so
No.
okay, I mean, in any case, I'm sorry that
We have put a better definition on this. Okay, but if we allow import, we just put minus, in all of this. So in some sense, the idea still is the same, but
Capital modular forms are section of omega k, such that vanish at the capital, no? So you have 2 divisors here, not SS, but the other one, I mean, is D. But the argument that you mentioned doesn't use order 1 or not. You should tell that we can hear it.
Well, I mean, he knows we can hear
Ah,
it,
yeah.
but probably he can talk.
Yeah.
Okay, so I agree that I'm confused with if it's mine, if it's a 4 or 0, but the idea is still the same in the sense that
Getting more poles or more zeros, okay? Let me,
Yeah, because you're thinking about functions. Yeah, functions over the a Riemann surface, a compact Riemann surface without poles, there are not. Yeah, but if you now you are using a differential, which is WK, you are taking is different than that functions. No, maybe that's makes sense. Of course, yeah. Yeah. But it's not a function, it's a section of a differential, no? I agree that if you take functions over a Riemann surface, a compact Riemann surface, you should have a pole, no? Because it divides, yeah. But if you take differentials, a section of differential is different, no? It's not a function over your Riemann surface.
actually, I think maybe could be a complement of that is that H1C. Yeah, so I think what he's saying, okay, so this is a divisor of, if it's, I think, negative degree, then there's no functions. But for example, one thing I wanted to mention is that I think this is true. H0 C XOR WK, I think. Let me just check. WK. So this is 0, okay? 0. These are the functions. This is the vector space, the trivial vector space. I don't know if this maybe, and the point is that H1 is not 0 necessarily.
No, but I think I'm really thinking about the modular curve, the total modular curve, Hx1, which is proper, no?
Yeah.
But the argument that he mentioned looks to work for functions, not for sections. I mean, if you take the structural shift, it's fine, but yeah.
yeah.
Yeah, so, okay, I think it does matter, but from the problem of this abstract nonsense, this is, okay, just put S or minus, okay, whatever this, putting this divisor here means. I also get confused, but I mean, from the poetical point of view, it seems more natural that it's not minus, it's zeros. Okay, so so I was talking about trying to prove something like this. Maybe okay, I don't think I will go too far, but in the arguments, maybe we'll see what is happening. Okay. So I forgot where I was. Okay, so in order to prove, so we have this definition. So what we want to prove is that it's locally finite. Locally finite. I use another color that I never, okay, whatever. Locally finite, okay? So this property that I won't recall, I will just say how what proposition will imply this locally finiteness? Okay, so I start with the morphism, with the correspondence, the basic one, just k minus ss, poles or 0, okay. P1 trig, I think it's called, upper trig, minus ss. So this is the correspondence that is used to define the TP, okay. And the proposition, okay, let me write it. The proposition that is 4.3, okay, is 4.3, 4.3, 4.3 in the paper, okay. So this is another proposition. The proposition that this map factors through P1 trig or exclamation mark k minus p plus k ss. I have all the parentheses, and this goes in this direction. So in words, TP factors. I won't write this, okay. I hope the diagram is clear enough, okay. So there exists, you know, there's like this, because this is the DP that we consider. This is a natural map, and we want to kind of show that goes inside this in this way. In some sense, this is telling us that, okay, what is this telling? That TP is putting more zeros or poles, okay, see the discussion. When we apply TP, we're putting more zeros or poles, because here we're putting more negative numbers. Yeah, that's kind of the idea. Yeah. So it maybe, of course, as we were talking about, this is for k less than 0 and n a positive or 0 integer. Okay. But actually, what I say is not completely true, because, for example, if k is 0 and n is 0, TP, these things at n equals 0 doesn't give you more poles or zeros. I don't know. But okay, this is something that actually play a role in the proposition I just erased. So remark, proposition 4.3 implies locally finiteness. Okay, so this is the key step. So this is the key property in some sense. With this, actually, it not only implies properly locally finite, also implies relations between the vector space, the cohomologies. Okay, the cohomologies. So this is really the key proposition. Now, since it's 12 and 5, I can stop here, I guess, and in the question I maybe can give more ideas.
Let's speak. Okay, there are questions to Héctor. Okay, if
I have a question.
Please.
It's probably like very trivial. It's just that I'm lacking understanding of. Okay, let's say it's a zero, it's a pole, it doesn't matter. But you add for each n, you add, let's say, a zero, so you want it vanishing on larger and larger degrees.
Yeah.
But then what does it mean to take the direct limit or the indirect limit? Which one did you say you're taking?
Yeah. So so I don't know. How do you call the limits?
Okay, which way does the arrow go?
Go is in this. So
In the opposite.
because
Okay.
I mean, what is this map in the nonsense explanation I gave? So I say that elements here are like A, B, okay, A0, A1, SS, B2, SS square, okay, where these are functions, okay? So if I put this, I'm saying, okay, I will stop at SS minus P plus K, okay? Here the corresponding. And the map is just forget everything until n. So A, B, S, S, blah, 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 B, N, S, S. So this map.
Okay, then it's really important that it's the arrow goes the left way.
Yeah.
And not the right.
Exactly.
Okay.
Yeah. Actually, if I consider not the compact support, rather the whole cohomology, this will be the other way, because yeah, okay, I mean, just wanted to say hi of x w odd, I guess. This is the colimit of h I x odd wk now positive. I will, this is n and e is fixed. So this is xi without the compact support, okay? This is the colimit. So this is for me, this is the limit in the arrow in this direction. So for me, if I put colimit, this is like the union of things. This is like putting together things. This is like the two, sides of the coin.
And
Because
when you add something positive to your divisor, what do you mean by that?
here,
Yes.
so pole or zeros. Yes.
So
this
you
is
just
pole.
flip
These are
it.
zeros, and this is okay.
Okay.
So this is like the other way around. And the idea that in this case, this is union of vector space, and this is a profinite construction of vector space. And these are very different, but similar, which is weird. But because the one is the dual operation of the other one in the categorical sense. But yeah, that's
But compact support is colimit or
limit.
Inverse limit.
Inverse limit.
And the arrow in the other direction.
So yeah, I mean, this is the in this direction, and the compact support ones is a limit in this direction. I don't know. I mean, this.
So then if the limits are like that, it would make sense that the negatives are zeros and the positives are the things that you add are poles, because if in the negatives you keep adding, like if you take a limit and you keep adding zeros, then I think Ariel is right, and then you eventually, like in the limit, get a function that vanishes everywhere.
But can you repeat?
So I think the point that Ariel was making was that, let's say you take the direct limit, the normal limit, of the things that you keep adding zeros to, then that thing, like you can't have many things like that. You can just have a thing that vanishes identically.
No.
If you have an infinite order zero that you've kept adding.
In this one, or in the other one, I forgot.
If you take the direct limit, then you
There.
practically say.
No, but it's the inverse limit in the compact support.
Yeah, so in the so it must be in the inverse limit, it must be zeros, and the direct limit, it must be poles. That's what I'm saying.
Good. I mean, because in this case, you say everything that live here must have some poles on S. S. This is what is kind of claiming. And
Again,
in this part, you say, I can have arbitrary large zeros.
yes,
Yeah. So I think this is what you're saying, yes?
yes,
Yeah.
kind of, I guess.
Should be zero, you say.
On the inverse limit side, yes.
This H zero is H1, no? But we care the most there.
Yeah, yeah. I'm just saying this is like the, the sections. It's the compact supported section of these sheaves on XOR 1, of course. Probably I forgot a lot of ones. Yes. So I was planning to say more, but I think this is, give you a little flavor. This is at least like, I give you like the abstract nonsense that implies what we want. Of course, this is where all the geometry and interesting stuff hides. So this is the real, modular core content. This is just abstract nonsense or something.
So the key is in proposition 4.3.
Yeah. Yeah. Maybe here, abstract nonsensely. Abstract nonsensely. Nonsensely. Probably that word doesn't exist, but here we don't use properties of cores. It just, we have this.
More questions? Yeah. Okay, if not, let's thank again Héctor